Okay. So flush with all that knowledge that we have now about constraints and how they work under the hood, now we can benefit and relax a little bit by using the Rbd Constraints from Rules tool. Now, essentially, and again, we just want to put this into our proxy thing here. Essentially, this is a very fancy, connect adjacent pieces node. It's in here, somewhere in there. It's in there, but it's doing that and a lot of other stuff. It's got like a lot of visualization things, but again, you can see the constraints being made, and that's cool. We can always make a null here and just look at the actual constraint output. It doesn't actually change anything about the incoming proxy pieces. So even though it is input and then output, it just passes through. But at any rate, so there's the constraints that it made with the default settings. Now, of course, we don't want the default settings. We want to change the connection type. Hey, look at that, hinges. Remember that? We were talking about that before? And remember service points before? Service points and hinges are exactly what we said they were. Both of them will make pretty decent looking constraints, but because of the nature of what we're doing, so there you go, that's what service point looks like. We are doing a deformation. We want to use hinges. And now you know what hinges are. And that's the benefit of understanding what's going on under the hood. Because this isn't, I don't think it helps to just read hinges here and assume why. I guess that's what you use. Now you know exactly why you use hinges for deformations. But yeah, it takes a little bit of time. And hinges have that funny characteristic of you not really being able to see them. Come on, come back to me. Well, when we're able to view these constraints, they're just going to look like single points. Because remember, they are basically scaled down to 0. I'm going to pause this for a minute. Okay, didn't need to. Strange. But at any rate, so yeah, it's the same kind of situation where it's like, well, where are they? They're not there. Well, middle click, they are there. They are still polygon lines. They're there. But they're just very, very small in between all of the little different pieces. Coming back to this for a second. And if you have a particularly slow computer, this is or even honestly, it's probably an average computer. This could be a good time to switch your Houdini to manual mode. And then that way when you click on stuff, it's not like reevaluating it all the time and causing your computer to be choking every time you click on something. Manual mode will allow you to click on a node and then say, I want to see this node. And you can click on, it basically says, don't do anything until I tell you to. So that can be a helpful way to still move around the interface freely without having to wait for it to calculate stuff every single time. I'm gonna stick with auto update because part of our problem right now is that it's making too many constraints. You can see that in our little visualization here. It's just positively fuzzy with them. So we can come on to the Rbd Constraints from Rules here, come down, and perhaps we should have even done this first before it made them all and caused everything to slow down. But one of the nice little bells and whistles of this tool is that it will say the maximum amount of constraints that we want. All right, so I'm gonna have to pause this again. 1 second. Oh, every time I threaten to do that, it comes back. Constraints per piece, -1. We don't want it to be -1. We want it to... -1 is a thing. Basically, that means either default to something else or don't have a maximum. Man, it is still kind of frozen, though. It's so strange. I think it's because I'm recording also, so... All right. So finally, we can do it. I'm going to say 4. So now it'll have much less. Now we should be in less of a stressful situation for our computer here. We can see these constraints in the normal manner by going to Rbd Exploded View, turn on Show Constraints, and actually have the constraint output plug into here. There we go. So yeah, there's a lot of constraints, but that's kind of what we want. We want a lot of constraints. We want, you could probably get away with less. 4, I think, is a pretty good compromise between having these hinges be very well represented in the sim, but not having so many that it's absurd. I should also point out now that the strategy that we're going to employ in this lesson is to not ever have these break. Instead, we will art direct where we want them to break. I don't want them to break on their own. You can have them break on their own. I find pretty much universally that it is worse. You'll get fractures where they shouldn't be, because again, none of this is really physically based in the first place. So kind of asking it to then will give me a physically accurate fracture, it's not going to happen. So it's much better, and in general, you're going to get notes from your supervisor or whomever saying, well, can we have it break here? Art direction is pretty much always the way to go, and don't rely on a dynamically generated break. So we'll talk a little bit more anyway about how to do that at the very end of the lesson, just so I'm thorough, but it is vastly superior to not rely on it automatically breaking. So the point is, it's not going to. These will never break, so think about that when we plan our fractures that are coming up, our art-directed ones. In the meantime, we've got these nice constraints, but these constraints don't have any properties associated with them. They're just constraints. They're just lines. We can also speed up the generation of these by saying like max search points. So I'm going to say max search points 5. So instead of being able to consider a lot more stuff, it's only going to be able to search through many less candidate points to generate these. And it's important because we're going to keep changing this fracture up here, which means it's going to keep changing the generated constraints down here. So I think it is very useful to make this run as efficiently as possible. So at any rate, so we've got all that. What I was trying to say was we've got constraint polylines, but they don't actually have any properties associated with them. So I'm going to make a Rbd Constraint Properties. This will kind of replace the wrangler that we did before, where we said the constraint name is this, and the strength is this, or the constraint type is this. That's what this will do for us now. So constraint type is glue. It's going to name it glue. It's going to have a strength. So now we're going to have these attributes on here. All that stuff that we made ourselves before is now, and then some, and now it's just going to populate those for us. So I'm going to keep everything by the default. Switch constraint type when broken. We talked about that. It's going to switch to soft. It has stiffness and the damping ratio and everything else. We talked about all these things. Plasticity, blah, blah, blah. Angular plasticity. We're just going to turn it all on right now. Leave it all at the defaults. We can and will, of course, change this soon. But I just want to see what it looks like so far. So come back into our sim. We need to actually put the constraint network in here. It doesn't really matter where you put it. I just like putting it after the solver for some reason. And let's make both of those things. We need to make our glue constraint relationship called glue. And we need to set everything to 1 because all those incoming attributes are going to be multiplied by these numbers. So we don't want to get surprised. So again, we also need the soft constraint relationship, same thing. Change everything to 1. Ones, ones, ones. Like so. Not the constraint iterations, leave those as they are. And merge them in here. And we should be able to see, hopefully. Oh, we actually didn't say this needs to do second context geometry. There we go. Now I can see the little dots have shown up everywhere. You can turn off the display geometry and you can see them. So let's see what we got. Let's do a little flipbook and we'll take a look in a minute. Oh, I thought I set this to. Okay, let's make this 72 frames, by the way. Good thing I noticed that. Good. 72 frames. Let's run a flipbook and see what that looks like.